let's conclude and kind of create an overview of what have we learned about decision trees. Decision trees are really the single most popular data mining or machine learning tool. The reason why decision trees are so popular is the following. First, it is very easy to understand the structure of the decision tree, right? It's even in a sense easy to explain to someone why the tree made a given decision, right? We can show them a series of splits and say, because of these conditions, this is the classification that has been made. Decision trees are also very easy to implement. Both the training stage is not that complicated, and also once we have the tree, it's very easy to use it for classification. So trees are also easy to use. Another thing that is important is that they are computationally also very cheap, in a sense that classification is easy. One caveat with decision trees is that it's very easy to overfit. So it's very easy to create complicated trees that are very deep and become too intricate and don't generalize well to unseen data set. And what is also nice about decision trees is that they can do both classification as well as regression. So decision trees have many good properties. Another thing that decision trees are very useful for is what is called learning ensembles, right? Many times it turns out that it is better to build multiple decision trees, let each of the individual decision trees create its own prediction, and then, for example, you use these predictions as votes or you average them together to make the final prediction. So this is what it means that you learn an ensemble of decision trees, and then you kind of take the individual predictions, average them up or somehow aggregate them to make the final prediction. So one method that does this is called bagging. The idea here is that we want to learn multiple trees over independent samples of the training data, and then prediction from each tree is considered. We average predictions from all the trees that we have and make the final prediction. It turns out that in practice, this kind of bagging approaches work much better, especially if the classification or the prediction task is very hard. So the idea is very simple, right? We will have our initial data set. We will create many random samples out of it, right? Let's call them D star 1, D star 2. This can simply be where we are sampling from D with replacement. This will give us a new set of training data sets, and for each of these, we then train a separate tree, tree 1, tree 2, tree 3, and then when a new example X comes in, we make each of the trees to give a prediction, and then we take the, let's say, the majority vote or the average to come out with a final prediction. So that is basically the whole idea of bagging. There are a few interesting things how we could use our Planet infrastructure that we just talked about to do bagging. So let's look at this. The idea is that here, right, the tree induction begins at the root, and that all the trees of the bagged model are pushed into the MapReduce queue. And then all the controller kind of has to do is to do the tree induction over a given data set of samples, right? One thing that we need to discuss when the data set D star is very huge, how do we create subsamples of it? Here, basically, the idea is to use hashing, right? So the idea is that I can take training records and I can use hashing. I can use multiple hash functions, and for every hash function, this creates me a separate different subsets of data, where the idea is that records that hash into a particular range, we use them to learn a tree. Right? This means that this way the same sample is used for all nodes in a given tree. And the way I define it right now is that this is sampling without replacement. What we want to do in bagging is to use sampling with replacement. So the way we can do this is by using multiple hash functions. To end our discussion of decision trees and of the machine learning topics, I want to also briefly compare the support vector machines and decision trees, and which of these two methods should be used in a given case. So support vector machines are generally used for classification, meaning usually binary classification is the most common case. They are used for real valued features, right? Because we think about a decision boundary in this Euclidean space. So they are not, for example, used for categorical features like colors or weather types or something, right? SVMs are also very good when we have hundreds of thousands of features, right? When you have lots and lots of features. So for example, for text classification, SVMs are really great. They also work really well when we have sparse feature sets. What this means is that most of our feature vector or most of our features take value 0. And what is nice about SVMs is that they have a very simple decision boundary. What we talked about is a simple linear decision boundary, which means it's very hard to overfit. So example applications for support vector machines are like text classification, spam detection, cases in computer vision where we are doing classification, and so on. On the other hand, decision trees are for in some sense, more building much more complicated decision boundaries. So decision trees are both used for regression and classification, having up to, let's say, 10 different classes if we talk about classification. Decision trees can handle both real-valued and categorical features. The most serious limitation of decision trees is that they can handle only hundreds of features, right? And only dense features, right? So when we think about decision trees, we think that maybe we have 10 or 20 or 100 different features, and for every training examples, all these features are filled in, right? And SVMs, decision trees allow us to come up with complicated decision boundaries. This is good. On the other hand, we have to be very careful because otherwise we will overfit to the data, so we need to do what is called early stopping. Some example applications for decision trees would, for example, be user profile classification, where we can have user, we describe each user with a small set of features, and now we would want to classify these users maybe as fraudulent or not, and this would be an example for application for decision trees. Another application would be, for example, predicting what is called on the web page bounce prediction, right? Whether a person coming to a given page, are they just going to leave the page or are they going to make the next click? In this case, again, we could describe every person with a small feature vector and make the prediction.